In section 3.1, I'm going to cover some of the important concepts regarding objects in free fall. To begin, I want you to get thinking about this race between three objects: a feather, a bowling ball, and a basketball. If we drop them from the same height at the same time, which one will hit the ground first? Well, we may expect that the heaviest object, the bowling ball, will come in first place, right? A heavier object falls faster than a lighter object, which means that the basketball would come in second place, and then the lightest object, our feather, is going to come in third place. Well, let's see what happens. Our expectation or our hypothesis that the order of them finishing this race would match the order of their masses was incorrect. So, what was going on here? Well, our observation was that the bowling ball and basketball both tied. They fell at the same rate. And then the last place was the feather. So, our observation was that the bowling ball and basketball fell faster than the feather. So, what was going on here? Well, all three objects all had the same two forces acting on them. They all had gravity pulling the object down. And we're going to spend a lot of time in this chapter and all year talking about this force, gravity. And the gravitational force does depend on how heavy an object is or how much matter makes it up. The force of gravity acting on an object is directly proportional to the object's mass. But there was another force that complicated the motion on these objects. The objects all fell down, so they all had motion that acted that was directed downwards. And there's a force that always acts opposite motion, and that force is what we refer to as drag. And the effect of drag was the greatest on the feather. The effect of drag on the basketball and bowling ball was roughly the same. And so, even though the drag was about the same, the mass didn't really matter for how quickly these two objects accelerated towards the ground. That's kind of weird. So, why does that happen? Well, we're going to explore that on the next few slides. When an object is acted on by only gravity, we refer to the object as being in free fall. And so we have to remember this definition: only gravity when we say that it is in free fall. And if we can say that an object is in free fall, then we automatically know what the acceleration is. It doesn't matter what their mass is, it doesn't matter what the velocity is, whether we throw it up, throw it down, drop it. All objects, when they're in free fall, only being acted on by gravity, all have the same acceleration. But our everyday experience, which takes place on Earth, near Earth's surface, is not free fall. Because when an object moves through our atmosphere, it experiences air resistance, and that doesn't fit our definition of free fall. So why do we spend time talking about free fall when we never really experience it? Well, under certain circumstances where there are certain factors present for an object's motion, the effect of air resistance is so small that we can ignore it or neglect it. And so we refer to the effects of air resistance as being negligible. And then the models that we're going to construct to understand free fall motion are going to very well match up with what's going on in the real world. So this is what we refer to in physics as an idealization, where we ignore details that make the math and concepts very very difficult to understand, and we focus only on simple cases. And the simple cases have easier to understand math, and it helps us understand the concepts a lot better. So, this fact that I just told you, that the acceleration of all objects in free fall is the same. Well, that's a really weird thing to consider. You may not have ever considered that a basketball and a bowling ball fall at the same rate. Well, what about the feather and a bowling ball? Would they fall at the same rate if they were in free fall? Well, I'm going to show you a video that's going to show this, that a basketball and a feather fall at the same rate.
Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now, in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So, in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCB 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Exact. They came down exactly the same. Wow.
Look.
Watch right there. Look at how they hit right there.
Exactly.
You're back on the side. I'll let the folks
Exactly
see
the
that.
same.
Feathers don't move, nothing.
Look at that. That's just brilliant.
Okay, so all objects, when in free fall, have an acceleration with a magnitude of g. Well, what is that magnitude? What is that value? Near Earth, g has a value of approximately 9.8 meters per second squared. This is the value that you're going to use when you do a lab. The objective of many Physics 1 labs is to measure the value of g. And when you measure the value of g, you're going to compare your measurement to this value. This is what we're going to use as the accepted value for g near Earth's surface. But when you do a test or when you're doing homework on positive physics, I want you to use 10. 10 is much easier to do math with, and so you can then focus on the concepts rather than the numbers associated with free fall motion. So for positive physics, we use 10, but the real value is closer to 9.8, so we're going to use that more precise value for labs. But we should know, and this is very important, that the value of g depends on your location. That value decreases as you move away from a source of gravity. The value of g on the International Space Station in orbit around the Earth is less than the value of g when we're standing on Earth's surface. And it's also different near other sources of gravity. For example, if you go to the moon, you'll experience a value of g that's about 1/6 the value of g on Earth. On the next slide, I'm going to show you a video of an astronaut from one of the Apollo missions in the 70s. And they did a demonstration of free fall motion. You're going to see him drop a feather and a hammer from the same height at the same time, and you'll see them accelerate together. right? Because they're both in free fall, and they're in free fall because the moon lacks an atmosphere. All objects around the surface of the moon are in free fall. But what you should expect to see is that they fall to the ground more slowly than an object dropped on Earth would fall. That's because they are accelerating more slowly because the value of g is less. Enjoy the video, it's pretty cool.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
Okay, pretty neat. Now we need to discuss some of the important patterns that you should expect to find for objects in free fall motion. When we have an object that is dropped from rest, and we should also note that this is what motion looks like for an object from its maximum height. So if you throw an object upwards, it reaches its maximum height and then it starts falling back down. Well, the falling down part looks exactly like this. So an object that's dropped from rest will fall downwards. So its velocity vectors, remember the velocity vector points in the direction that the object is moving, is going to point downwards because it's moving downwards, and they get longer. Remember, the length of the arrow indicates the magnitude of the vector. And so the magnitude of the vector, or speed, is getting much bigger as an object falls. And that's because the object's velocity vectors and acceleration vectors are in the same direction. Now, what about a graph of velocity versus time? Well, the thing to remember about this is that the slope of a velocity versus time graph gives you the acceleration. Well, an object that is in free fall will have an acceleration equal to g. And if we define up as our positive direction, then down would then be negative. So we should expect that a coordinate system where up is positive, an object that's in free fall should have a velocity time graph with a slope equal to negative g. And here the slope is given a value of 9.8 meters per second squared. What about upwards motion? Well, upwards motion will feature an object whose velocity vectors point upwards. But since the acceleration is down, any object that has a velocity and an acceleration that are in opposite directions are going to decelerate. It's going to slow down. And so you see the velocity vectors are getting shorter. That's indicating that an object moving upwards is slowing down. In this example, we have an arrow that's launched vertically upwards, and it moves to a maximum height and then falls down to the ground. Now, if something is launched vertically upward, it doesn't move side to side like like this graphic would suggest, but it's really difficult to show that if it moves up and then it moves back along the same path. It's a lot easier to show if you curve it a little bit. So the trajectory just means the path is noted, and it asks to rank the acceleration. So if a problem asks you to rank something, it means to order it. So the acceleration of the arrow, when the arrow is in the air, it's in free fall. And what's the acceleration? Well, it's equal to g. So the acceleration is g, and it has a direction down, and it's the same at all points. So it's the same at all 5 points. And so if you are doing a ranking task for me, and you want to indicate that the acceleration at points A, B, C, and D are all the same, all you have to do is put an equal sign. That indicates that the value is the same at those 5 points. In this example, we're asked about the same exact situation, but now it's asking us to rank not the acceleration, but here it wants to rank the speed. So the thing to notice here is that points A and E are at the same height. Points B and D are at the same height. And point C, this is indicating that it's at its maximum height. Well, the maximum height is a turning point, and the velocity and the speed of an object at a turning point is 0. So that means that C is going to have the least speed because it's 0. Can't get slower than 0. Now, what about comparing points A and E? Well, A and E are at the same height. Now, for objects in free fall, if they have the same height, then it's going to have the same speed. Objects in free fall at the same height have the same speed. Okay, what about, so A and E are going to be tied, B and D are going to be tied. Well, obviously, as we move upwards, the object becomes slower. So B and D are going to be tied for, I guess you would describe it as second place. So we're going to write B and D are tied with each other. And the speed for B and D is faster than C. So we'll put a less than sign in between C and B. That's indicating that the speed of C is less than the speed of B, which is equal to the speed at point D. And these two speeds are less than the speed at points A and E. So here is our answer for ranking the speeds at those 5 points. In this example, it's the same scenario, but here we want to find the velocity versus time graph that matches this motion. So you'll notice that the wording here, it says to ignore air resistance. That is telling us that the object is in free fall. And that tells us that the acceleration is g, and we're just going to assume that they're calling up the positive direction. We would have to assume that because the arrow is fired up, and you can notice that the initial velocity for all 5 graphs is positive except for this one. And it can't be that one because this one starts from rest. So up is the positive direction, so the acceleration has to be negative. And remember, on these graphs, the slope of the graph tells you the acceleration, so the slope we should expect to be negative g. So the only graph that fits that description is graph D. Graph D shows a graph with a slope that is constant, because we have constant acceleration, and it's a negative value. So graph D corresponds to this motion.